Hi class, welcome to our next section, our next chapter actually. This is chapter 3. We're going to cover 3.1, which is linear models. This section, this whole chapter really is like a mixture of chapter 1.3 with all of chapter 2, right? All of chapter 2 except for the numerical methods. So this first section, we're basically going to be creating linear models and then using the methods that we have from chapter 2 to solve them. So we're going to solve either by separation of variables, finding an integrating factor if it's in a linear form, or trying to find an exact equation, right? Solving it with the methods of exact equation where we are using those partial derivatives, okay? So we're going to go over a couple examples. Some of these we've seen in the 1.3 video. Some of them were talked about just briefly. And then the examples that I did from 1.3 were something that were completely different, things that I thought were more difficult because they just were. So we're going to go and we're going to review some of the stuff that we saw in 1.3 where maybe we just derived the formulas, but we didn't actually do an example of those. You probably had an example of them in your homework though. They're probably seemed difficult to you at the time because nobody likes word problems, right? So let's go ahead and get over this, right? So for example, let's say we have a small metal bar whose initial temperature was 20 degrees Celsius, okay? It's dropped into a large container of boiling water. How long will it take the bar to reach 90 degrees Celsius if it is known that its temperature increases 2 degrees in 1 second? So this is a Newton's cooling problem, right? Where we're not cooling, we're actually increasing in temperature, right? So it's the same form. It's just that our constant K that we had in that formula that we saw in chapter 1.3 will be a positive because we are now having a growth instead of a decrease, right? We are increasing to an ambient temperature rather than decreasing to an ambient temperature. And if you look here, it looks like we have a rate of increase, right? It increases 2 degrees every 1 second, okay? So again, this is going to be Newton's law of cooling, right? Which is the derivative of the temperature at time t is equal to a constant times the temperature function minus the ambient temperature, right? The temperature of the medium. So here our initial value is 20 degrees Celsius, right? That's our initial temperature at time 0. The ambient temperature is 100. Boiling water is 100 degrees Celsius, if you did not know. Freezing is 0 degrees Celsius. And the rate of change is 2 degrees for every 1 second. However, this is an error in our thought process, okay? This is not the instantaneous rate of change, right? Instantaneous rate of change is your derivative, right, at whatever time. So we cannot say that d of t is 2, right? However, it does give us a secondary point to allow us to do some calculations, right? I know that at time 0, I'm 20 degrees Celsius, and 1 second later, I'm at 22 degrees Celsius. So I have a secondary point, which is going to be helpful for me when I do my calculations, okay? So it would be an error for you to think that the instantaneous rate of change here is the constant 2, and setting up 2 equals yada yada yada. It's not going to work, right? So we have the change in temperature at time t, right, is equal to K times t minus 100. So we got that from our Tm, right, which is the ambient temperature of 100. So that's the equation that we have. So when we solve this, right, which we can do by separating the variables, right? There is no little t variable, so that's nice. We can take the big T variable and move it over. We can keep K over on the right side if we want. We could have brought it over and kept it in the denominator on the left. It doesn't really matter, although for simplicity, it's easier just to keep it, right? So this is nice because we can do a very, very basic U substitution here that doesn't really change anything. So this really just turns into the natural log of t minus 100. And this turns into K times t plus c, right? Very, very easy integration on both sides. So now we can start to solve for t, right? Because ideally, this is the function that I want. and then we can start using the conditions and the values that we have to start solving for these unknown variables that I have. So I need 2 points here because I have 2 unknowns. That's why it's nice that I have some extra information to give me an extra point, because one of these will allow me to find C, and then using both those in conjunction I can find K, right? Or vice versa. We'll see how it goes as we do the math. But before I do all that, before trying to do it now, it'll be way easier to just raise both of these to the power of E, right? So the natural log cancels, and this becomes E to the power of KT, right? So I got constant multiple of E to the KT. Here the natural log cancels. Then I can just add 100 to both sides, and this is the general form of my function. So now that I have a general form, I can use 0 and 20 to find out most likely this C value. Well, it will be C. And I can use the 1 and the 22 once I know C to find my K. Okay, so that's nice. So 0 and 20 will reduce my equation down to this. So C is negative 80, not 180. Negative 80. And then using this value with this function, right, using that constant of negative 80 that I found, I can then solve for K, right? So I subtract 100 here, and I divide by negative 80. So subtracting by 100 makes this negative, dividing by negative 80 makes it positive. I can reduce this down if I want to, it doesn't really matter. But K is basically going to be the natural log of this thing, right? So properties of natural log, give me a constant. Now, if we want to, we can get an approximation value, but things are always easier when you have an exact value, right? So even when I put it here, I can use this to simplify to something that's even easier to deal with, right? Because the E and the natural log cancel. Whereas if I kept K as a constant, well, it is a constant, but a decimal approximation, I would have kept it in the exponential form, which is fine, right? But this will probably be a little bit easier to deal with, especially since I can reduce to 70 and 80. Okay. And so I get the following, right? So this 90, because my question, right, is how long will it take for the bar to reach 90 degrees? Okay. I'm now using, let's go back here. This is the T of T function that I'm going to use, right? This is basically it in its simplest form, right? I probably should put another therefore T of T equals this equation, but that's the one that we want to use, right? So now I want to know when my rod will reach 90 degrees Celsius. So that's the output I set it equal to, and then I just solve for T. Very, very straightforward. Okay, so I subtract by 100, so I get negative 10, divide by a negative 80, gives it positive, makes it 1 over 8. And then now I can solve this by just taking natural log of both sides, okay, and then solving for T. And so this is the exact form of the equation. The only times I want decimal answers in this class at all is when you are doing a problem like this, which is an application problem, because this as an answer makes absolutely no sense. So definitely 100% give your answer as a decimal approximation. If you want to be extremely safe, give it to 4 decimal places, okay? Really, you should know how many decimal places you need. So it's 82.13 seconds because that makes sense. It really doesn't make sense to give me 4 decimals of accuracy on a time, right? However, it also doesn't make sense for you to round it to 82 seconds, right? So don't just be like, oh, I'm going to get rid of all my decimals. My students always have a hard time with decimals and rounding. You always want to round everything away. You don't really want to round everything away, right? So think about what decimal spot is appropriate. Generally 1, 2, or 4 is where you want to have. 3 really doesn't make sense. It'll generally be 2 or 4 decimal places, right? In this case, this is how many we would want. Okay. All right. So reflecting back on decimal places real quick, the standard really is however many decimal places you're given. In this case, none, right? You want your answer to be 1 place more of accuracy. So since we were to the ones place, we would want accuracy at least to the 10th place. If you give me 1 extra, that's relatively safe. Okay, so that's really the standard. So let's move on to another example. Okay, so we talked about this example in 1.3, although I didn't have any visuals for you, and it may have been sort of convoluted because I didn't have anything for you to look at. So we're just going to do an example now to make it a little bit easier. We're going to take a large tank. It's going to be filled to capacity with 500 gallons of pure water. Okay. A brine mixture that is 2 pounds of salt per gallon is going to be pumped into the tank at a rate of 5 gallons per minute. Right? We're going to assume that the solution is pumped out then at a rate of 10 gallons per minute. So the amount that we are coming out is more than the rate that we're coming in, right? So ideally, it makes sense that sooner or later, our tank is going to end up being empty, right? Because it's draining or being pumped out faster than something is flowing in. So we want to find the number, A of t, of pounds of salt in the tank at time t, right? And we also want to know when is the tank empty. So we want to find a solution to this equation, to this example, and then we want to analyze it for when there's going to be nothing left inside the tank, right? Just a heads up, if you don't have your notes handy from chapter 1.3, I would say to pause the video and go ahead and grab those or read through them real fast. Just kind of so that you're aware of what we're using and the formulas that we're going to use. I'm going to repeat them, obviously, but it's nice that you're familiar with what we're about to go over before we do it, right? So, let's see here. So this is a picture of what we're going to be using, right? So we have a 500 gallon tank. So when we start off, right, our initial value is that we are 100%, right, full with pure water. So there's 0 brine solution. So at time 0, the initial value of the function that we're trying to find here, the number of pounds of salt at in the tank at time t, is going to be 0, right? Because it's pure water. And then we have an input rate of 5 gallons per minute with a solution that contains 2 pounds of salt per gallon, right? And we have an output rate of 10 gallons per minute at a amount that has, we don't know, right? It's not specified what it is. That's part of what we're trying to solve for, okay? Because however much salt is in at any time t is the concentration in the outflow, right? Makes sense. So remember that this was the equation that we had, that the rate of change of the amount of salt that's inside of the tank at any time is the rate of the amount that's coming in minus the amount that is coming out, right? And so again, we have to look at not only the rate, but the solution in that rate, right? It's 2 pounds per every gallon, and it's 5 gallons per minute, right? The outflow out is whatever the rate A is at 10 gallons per minute, right? So remember the equation we had for the rate in is the concentration in our inflow, which is 2 pounds per gallon, times the input rate. So it's 5 gallons per minute, right? So for every minute, we basically have 2 times 5, right? So 10 gallons are coming in every minute, okay? So 2 times 5 is 10 pounds per minute, right? Makes sense. Our concentration in the outflow, or rate out, I should say, it's the concentration in the outflow times the output rate of the mixture, right? So here, the concentration in the outflow at time t is the amount of salt in the tank at time t, which is our function we're trying to solve for, right? Divided by the total amount of solution at time t. So the total amount of solution at time t, this denominator here, is going to be given by whatever my initial amount is, right, which was none, plus the input rate of salt minus the output rate of salt, right? So the input rate and the output rate, not the concentration, but the input rate and the output rate at time t, right? So here for the rate out, I have 500 gallons, and I'm going to add to that I have 5 gallons coming in, and I'm subtracting out 10 gallons coming out for every minute that passes, right, times the concentration, or I'm sorry, the output rate of the mixture, which is 10 pounds per 10 gallons per minute. Okay, so this is going to give me 10A over 500 minus 5T. So again, this is the total amount of solution at time t, regardless of if that solution has any amount of salt in it or not. Okay, so it starts off with 500. That's how much stuff is in here of pure water with no brine in it at all. Okay, so remember this A function that we're looking, that's the concentration of the solution we're trying to find, right? How much salt is actually in there divided by how much liquid is in there total. Now it's draining, so that's why I start off with 500, and then I have 5 gallons per minute coming in, and I am having 10 gallons per minute coming out for every minute that passes, basically, right? So overall, I'm losing 5 gallons per every minute, right? Makes sense. And then times the concentration of the outflow. So this is my differential equation, right? The rate of change over time of the amount of salt in my solution is going to be 10 minus 10A over 500 minus 5T with an initial condition of 0 at time 0, since it's full of pure water. So this is what we want to try to solve. Notice that if we try to use separation of variables, it's not going to work too well. I can add, I can subtract 10 on this side, and then I can multiply it by this, so I guess I could use separation of variables. Let's see how this will work out. Oh no, because I have the A here. So it looks like it's going to be in the form of a linear equation, right? So I want to try to use my integrating factor method. Okay, again, the separation variables wouldn't work, because if this was a 10 over here and I multiplied by this, I'd have the t with the dA, and then I have to multiply by dt. So then I would, right, it's always going to be mixed up. The t will be with the differential of A, and the A variable will be with the differential of t. Even if I start to try to manipulate those back and forth, I'm never really going to be able to separate them out, right? So I can just add this over, and then it's in the form of a linear equation, right? Where this is my P function, and this is my Q function, right? P of T, Q of T. So you can tell right away that this is not a perfect, this is not the product rule, right? So I'm going to have to use the integrating factor. Okay, so my integrating factor is e raised to the power of 2 over 100 minus t. Now you might say, well, where did that come from? Well, look at my numerator and denominator. 10 over 5 is just 2. So you just simplify that before we throw it in there. We can use our u sub so that we have the 2 on the outside. 1 over 100 minus t. The substitution will be 100 minus t. So it'll end up being negative. It'll be a negative 2 times the integral of 1 over u du. So I will end up with e to the negative 2 natural log 100 minus t, right? Right. So I talked you through it. You should definitely be familiar with doing that by now at this point, especially since it's a Calc 2 review kind of problem. And then e raised to anything cancels each other out, right? So remember, negative 2 is an exponent. So this will just turn to 100 minus t to the power of negative 2, right? So that's my integrating factor. I'm going to take this thing, and we're going to multiply it times my entire equation here. So times the dA dt times this part, which is nice because it'll help us to not necessarily cancel stuff out, but it'll do something, and then times the t here, right? So I have this now more complicated looking problem, but that's fine because this left hand side is actually just a product rule, even though I don't have to be able to see it right away, right? I know that the part that's attached to the dA dt part is one of the terms, and then the variable part is the other term. So this extra part and this dA dt basically just go away. Then I can start doing some work over here, right? So this turns into d over dt, this first part, this last part here. If I start to try to integrate this with respect to t, it looks like something that we're used to already, which is this is basically 1 over 100 minus t squared. So we're going to want to use a u sub by that point. So we can go ahead and take this and when we find our du will basically be negative dt, right? So we want to get rid of the negative part, so we'll throw it in the front. So when we put this as an integral, it would be negative 10 integral u to negative 2 du, which is easy to integrate here. When we integrate this side, the d dx is just going to fall off, and we'll have a times 100 minus 2 to the negative 2 power. Then this will turn into a negative, which is fine. So I'll turn this positive, and then our power will change to a negative 1. So that's nice because we don't really have to do too much over here, right? So integrating both sides, this is what we get for the left-hand side. The right-hand side, this just changes. It changes positive, and we get our constant of integration. Now, remember, we're trying to solve for a, so the easiest thing to do is to divide by this, which is a terrible idea, actually, right? We're just going to multiply with the opposite power, right? So we're going to multiply by 100 minus 2 squared. So that will boost this one up a little bit, and we'll get c times 100 minus t squared, right? So that's not too bad. Now a is isolated. Now from here we can pull out a common factor of 100 minus t. So we have that on the outside, and on the inside we'd have basically 10 plus 100c minus tc, and that's fine. Or you can do something a little bit different. So here it looks like I didn't actually factor, which is crazy to me because I always just factor stuff out. So it looks like I actually expanded this whole thing out. Terrible, terrible idea, Professor Williams. Why did you do that? But that's fine. So we still have this polynomial. Again, if I wanted to refactor it, I would have just pulled out 100 minus t if I was a little bit smarter. But that's fine. So from here, I can now start to use my initial condition to try to solve for this constant, right? So when I plug in 0 everywhere, even here is fine because this goes away, this goes away, this goes away, and I'm left with this equaling 0, right? Which is nice because it's still a simple equation. However, it would have been even easier if I just pulled out a factor, but whatever, right? So 0 is 1000 times 1 minus 10c, so here I factored, okay? That gives me c is negative 1 over 10. Sorry, I meant 1000 times 1 plus 10c, and then I get c is negative 1/10. So using that and plugging it back in, that's going to turn this into a positive 1/10 t squared. This is going to turn this into a positive 20t. This stays the same, this stays the same. This turns into a negative 1000. So 1000 minus 1000, that cancels. And then these t's add up. So plus 20 minus 10 leaves me with a positive 10. So my equation for the amount of salt that is in the solution at any time t in my 500-gallon tank is given by this equation, right? Now this was just part of it, was to find this solution. The other part was to find when is this going to equal 0? How long does it take for our tank to be empty, since I'm draining more than I'm putting in, right? So it's a very simple quadratic, so solve it by any way you know of solving quadratics, but you should get t equals 10. So the easiest way is to factor out 1 over 10t, right? So that leaves 0 here and 100 here, and then it's very easy to solve. So I didn't go through the process because you should 100% know how to factor and solve this if you're in differential equations, okay? Don't throw this into quadratic formula. It's not necessary, right? I mean, that's just a perspective of mine, but I see people try to solve easy quadratics and then they use the quadratic formula. Way more work to use the quadratic formula than it is to just factor, right? Even if you factored only t out, it's still very simple to try to solve this. So you don't need quadratic formula for everything, right? Work smarter, not harder. It's always the motto in math. Therefore, it will take 100 minutes for the tank to drain completely. Okay. Now we got one last example. It's an example of an LRC system, right? LRC circuit, or I guess an RC circuit. Sorry. So we have a 200-volt electromotive force is being applied to an RC circuit, right? So this is basically the incoming voltage, right? The resistor has a resistance of 1000 ohms. the capacitor has a capacitance of 5 to 10 to the negative 6 farad, right? So we want to find the charge Q of t on the capacitor if the current at time 0 is 0.4. Okay, so we want to determine the charge and current at t equals 0.005 seconds. Okay, so we also want to determine the charge as time goes to infinity. So here is our RC circuit. So the impressed voltage starts here, right? So this is where we apply the voltage, and it goes around our resistor and circuit. It comes back to close the loop, right? So the voltage drop across here and here needs to add up to 200. Okay, so voltage across the system is E of t, which is 200 volts. The current is I, which we know is the same as the first derivative of Q. Okay, the voltage across the resistor is IR, which we can then replace in terms of the charge as R times dQ over dt. And the voltage across the capacitor is 1 over the capacitance times the charge. Okay, charge function. So we want to, or the sum of voltage across the components in the circuit must equal the total voltage across the system. So as I just said, this plus this has to equal 200. Okay, so 200 is I times R plus 1 over CQ, and we can replace this into terms of all of Q, right? Now this is the dE that I have. So if you notice, this was just an equation, but it was not a differential equation. So now I got a derivative in here. It has to do with the rate of change. So I can now replace my resistance and my capacitance, and I can isolate my dQ term if I want to. But if you notice, it's actually in the form of a linear equation, right? I have something times dQ plus some other function times my Q equals some constant. So the only thing I'd really have to do here is divide everything by this leading coefficient term that we have, and then I can find my integrating factor, right? So there we go, right? So divide by 100, divide this by 100, takes off by 1,000, okay? Takes off 3 of the zeros, so now I'm just at 200. Much easier to look at in this form anyways. And I can start to move things around, right? So I can try to solve this by separation of variables, which is, it looks like that's what I'm going to do here instead of using my integrating factor. Okay, mainly because I don't have any functions of t in here. It's just a whole bunch of constants, so I can separate. This is not a function of t. This is not a function of t, right? So I'm going to pull out the weird factor so that I have all constants on the inside. All right, so that's going to multiply that by 5, and then I can start to divide this out. Oops. Okay, you can divide this on both sides. I can start to separate both sides. So now I'm really going to have only dt on this side with the 1/5, and then this is going to be my denominator on the other side. So here I'm going to have to use the u sub, but integrating 1/5 with respect to t is very, very straightforward. I don't even have to write the integration symbol. You guys should know what's happening here, right? So this just bumps up. Then I have my constant of integration. This is basically going to turn into natural log of 1 minus 1,000 q. Sorry, it'll be negative 1 over 1,000 natural log of 1 minus 1,000 q, right? Because that u sub I'm going to have. So from here, I can now start to isolate q because q is my function, right? T is just the variable, q is the function. So I can raise everything to the power of e. Let me get this out of here, right? So I'll raise everything to the power of e. This turns into an exponent. The natural log will cancel out. So I have 1 minus 1,000 q to the negative 1/1000th power. This turns into e to the c, which is just a constant. And then this will turn into e to the 1/5 t, right? So c e 1/5 t. Then this is just the inside of the natural log with its exponent. Okay. Here I will multiply, raise both sides, to the power of positive 1/1000th, right? So that will change out this value. My apologies, not 1/1000th, but times to 1,000th power. Okay, so this bumps up by 1,000, by negative 1,000, I should say. So here, I can now get to my function, q, and this is what this exponent looks like. And then now I can solve, right? So I'm going to add 1 divide by, subtract 1 divide by negative 1,000, so that turns that to a positive. And each time that I do this, right, c divided by a negative 1,000 is just another constant, right? I don't have to keep doing math on this. It just keeps turning into another constant. So this is my actual function here, okay? Now the question wanted me to find a few things. Find q of t, which I did. Find the q of t on the capacitor if this is my initial condition, okay? And I want to determine the charge and current at this time, and I want to determine the charge as t goes to infinity. So there's quite a few things. There's about 5 things here it wants me to find. So let's go through here and use our equation, okay? So I is the first derivative of q, so I can use that to find the first derivative of q, and then I can use that initial condition to find that constant that I have here, right? So 0.4 is negative 200c, solve for c. Never ever ever give me this as an answer, right? Do not have a decimal inside of a fraction. It does not work that way. Give me either a simple decimal or a simple fraction, okay? So here you can replace 0.4 with 4 over 10 and then do some fraction work here and get down to negative 1 over 500, right? This is preferable over decimals any day and any time. So this is my function now, q of t with c solved for, right? And then I can pull out a common term of 1 over 500 if I want to make it a little bit simpler, so I don't have crazy fractions everywhere. So this is a little bit easier to work with, okay, but it's really up to you, right? So at time equals 0.005 seconds, I can just plug that into my q of t, right? And I get about 0.003 farads is the charge, right? Because farads, okay, capacitance is farads. So the charge is 0.0003. Okay, and the limit of this as q goes to infinity is going to be 1 over 1,000, right? So if I'm looking at my function, as this goes to infinity, this part pretty much just dies off, and I'm left with 1 over 1,000, okay, or 0.01. Now, I noticed this after I made it. I forgot one of the questions here. You can figure out pretty easily if you want to do that, right? Which is the current at time equals 0.005 seconds. It's the only thing that I didn't find out. So charge on the capacitor we did find. Actually, we didn't find the charge on the capacitor. Charge on the capacitor would be this value, and then here we go. Would have been this value, right? That's the charge, and then charge on the capacitor would have been this times 1 over the capacitance, right? So that's how we would have figured that out. And then to find the current at t equals 0.005 seconds, I would have just plugged in 0.005 to my I of t function, right? So I don't need to solve everything here because the rest of it's trivial, basically, right? But that's what we're doing in this section. We are creating models, and then we're solving them with the methods that we know.